Welcome and thank you for joining us. This event will discuss how the use of hydrogen in internal combustion engines can help decarbonize various sectors. We move to the next slide. Thank you. During this event, all participants will be in a listen-only mode. To ask a question at any time, please submit your question using the Q&A button at the bottom of your screen. We encourage you to ask questions at any time. Questions will be addressed when possible. This event is being recorded. The recording and presentation will be available on the Engine Technology Forum's website shortly after this live event. I would now like to introduce our first speaker, Alan Schaefer, who's the Executive Director of the Engine Technology Forum. Alan?
Thank you, Josie. Welcome and good morning, good afternoon, good evening, wherever you might be joining us from. We're delighted to have you with us today, and we have quite an expansive group. Just taking a quick look at our pre-registration list. Today, our audience, all of you are from the United States, India, Japan, and Europe. We have representatives from the academic community, universities, non-governmental organizations, including trade associations and environmental groups. The United States Congress is represented, both the House and the Senate committees, Department of Energy, a number of cities in California, state government agencies representing the states of California, Minnesota, Maryland, and Delaware, a number of research institutions, industry and financial analysts, our friends in the media, and of course, many colleagues from industry, engine and equipment, OEMs, and suppliers. So welcome to all of you today. We're delighted to have you with us. Today's session is brought to you by the leaders in advanced engines, equipments, vehicles, components, and fuels, all who are members of the Engine Technology Forum. And you're going to hear from a number of those here in just a moment. A quick word about the Engine Technology Forum. We are a not-for-profit educational association, and it is our mission to bring together folks for a discussion in forums like these to discuss the issues of the day relative to internal combustion engines and the fuels that they use. So a little bit about us there. As we look at the energy future, we see one of a great mix of fuels and technologies, certainly more diversified than today, using electricity, using hydrogen, biofuels, and advanced internal combustion engines. Those powered by gasoline, diesel, natural gas, and propane. And those are tightly woven into the fabric of our global economy, and in many ways in many different sectors. And today we find ourselves in the midst of an energy transition. On the one hand, we have an energy system that relies heavily on fossil fuels. On the other hand, we are working towards a system of reduced carbon emissions and energy systems reliant wholly on renewable energy. Internal combustion engines uniquely have one foot in both of those worlds, and that is one of the incredible advantages I think we have going forward. And our panelists today will talk about the reach forward with some of the opportunities to reduce carbon emissions from internal combustion engines. We see the future for ICE as being one of achieving lower emissions, increased efficiency, and a switch to sustainable and renewable fuels. And at the end of the day, we also see it very much as a key part of the energy future. And now I'd like to also announce that we are releasing a white paper today, Opportunities for Reducing Carbon Emissions Using Hydrogen-Fueled Internal Combustion Engines. This is available in the resource section of your Zoom toolbar. You can download it there anytime today, and it's also available on our website. And this discussion, we're going to discuss many of the issues in this white paper today in greater detail. But let me now introduce Dr. Amaya Joshi of Mobility Notes, and he is the author of the white paper, to offer a few comments about the paper and its findings. Amaya?
You bet. Thanks, Alan. Hi, everyone. Nice to be here. And I just want to say a quick thanks to Alan for inviting me to do this white paper. I had a lot of fun doing this. For some of you who may know me, I specialize in actually covering broadly the transport decarbonization sector. I've spent a lot of years working on emissions control and then engines and hybridization, electrification, and so on. I go to a lot of conferences, read a lot of papers, and one thing that definitely stands out in the past few years is that there's just so many technologies we are all advancing. There's so much room for a role for all fuels to participate in decarbonizing the transport sector. It's a hard problem, and we certainly need new fuels to address decarbonization. We're not going to have one technology that solves the problem, right? And so hydrogen does have a very significant role to play. So I did try to pull together a summary of what is the background, what is the current status, what is the future challenges for hydrogen as a fuel in decarbonizing transport, and that's what this white paper does. I'll keep my comments short. I know there's a lot of good content to follow, but just wanted to run through some of the main topics. So you can see the table of contents here. Again, I go through the background, technology overview, give a literature review of the advances in this technology, move on to the emissions control. That's going to be very important for upcoming NOx regulations, for example, and then very key considerations of cost, infrastructure, and life cycle GHG reduction potentials, right? If you go to the next slide, I just have one slide which I just want to kind of set the stage for the next speakers, which is that, I go to, again, as I said, I go to a lot of conferences, and now there's always a big section devoted to H2-ICE, and you can just see in this one chart that I've taken from an FEV talk, which is that there's almost all major manufacturers have some level of effort going on hydrogen internal combustion engines at various stages of development. And you can just see in this chart, there's several engines in development, whether they are port fuel injected, direct injected, whether they are for on-road or off-road applications, all sorts of engine displacements, right? And so really that's a massive amount of work that's being done. And again, I've just tried to cover the various aspects of this development. So of course, the first thing that drives this industry is regulations and policies, whether it's reducing greenhouse gas emissions or reducing criteria pollutants. And so that is one of the key drivers for hydrogen use. The engine technology, it's advanced quite a bit, but there's also a lot of work still being done on improving the efficiency of the H2-ICE. Fuel injection strategies are a critical part of this, and that's why I've just highlighted that on this one. NOx control, as we are moving towards near zero NOx levels, and especially with the EPA and Euro 7 emphasis on almost 90% reduction in NOx, hydrogen does have NOx emissions, and that's a critical one to control. And Luis will be giving a very good overview on all the various off-treatment controls that are being brought to bear on this topic. And then finally, there are some real challenges, right? The fueling infrastructure has to be built, and the cost of the fuel and the infrastructure has to be reduced. So that's there. And then finally, life cycle considerations. At the end of the day, we have to reduce greenhouse gas emissions from a well-to-wheel or a cradle-to-grave perspective, and that has to be discussed here as well. So again, very briefly, I'm covering all of that in the white paper. Please download it and send any questions you may have to Alan or me, and we'll be happy to address those. So thank you.
Thank you very much, Amaya. Really appreciate that. And again, please take a look at our white paper that is fresh off the press today. So without any further ado, let me just talk about what happens next. So we're going to explore the following areas related to H2-ICE. We'll delve into the technical considerations of both the fuel and the engine. We'll look at some of the operational issues for different sectors and applications, talk a bit about economics, and then policies and the issues, excuse me, that impact the future for H2-ICE. And so the way we're going to work today is we're going to start off with some opening remarks from each of our panelists, and then we're going to get into some specific questions and discussion on both the fuel and the engine, and we'll have time for your questions as we get to the end. So without any further ado, let me introduce our first panelist, who is Jim Nebergall. Jim is the Executive Director of Market Strategy in North America for on-highway applications for Cummins. And I think Jim is joining us today from Columbus, Indiana.
Yes, thanks, Alan. Welcome.
Welcome. Thank you.
Thanks for having me. So I'm looking forward to this discussion. It's a great topic. I've been involved in the hydrogen combustion work at Cummins for about 3 years now. So really excited for this discussion. Thanks for pulling it together. And Do you advance the slide for me? All right, perfect. So just a quick background on Cummins. We are organized as 5 operating segments, with an engine business having engines less than typically 16 liters as one segment, and then above 16 liters as in our power systems business. We also have a components business that has components that are used on engines, Cummins engines, and competitor engines, as well as brakes and axles with our acquisition of Meritor. We have a distribution business as well to support the products in the field, and then also a zero emission business called Accelera by Cummins, which has battery electric fuel cells and electrolyzers. Today, we're going to be focused on the hydrogen combustion engine, but before I get there, I wanted to reiterate our Destination Zero strategy, and that multiple energy sources will be required to truly decarbonize. That means energy sources, low carbon fuels, a decarbonized grid, and green hydrogen, as well as multiple power solutions, including advanced combustion engines, battery electric, and fuel cell. We need diverse solutions. This is a very hard and challenging problem to decarbonize these sectors, and there will not be one single solution. Okay, next slide. As we narrow into the hydrogen topic, Cummins is investing in the ecosystem, the entire ecosystem for hydrogen, including production to produce green hydrogen from renewable energies. Storage solutions is a very critical technology that's also required to store this critical gas. And then there are two consumption technologies, fuel cells and the hydrogen combustion engine. Next slide. So we do view these as complementary solutions. A lot of people they see it as competition between a fuel cell and an engine, and they're quite complementary. And so I'll talk about that as we go through. Okay, next slide. And so at a high level, hydrogen is within reach. It does support the decarbonization of the commercial industry because it is zero carbon well-to-wheel with green hydrogen. So if the energy used to create the fuel is renewable, it's a well-to-wheel story of zero, and a tailpipe story for zero. So zero carbon at the tailpipe, zero carbon well-to-wheel. We can be at scale production in the decade because it's conventional technology. We know how to make engines, and you're going to hear it from multiple companies. We know how to make engines run on this fuel. And it was part of the EPA greenhouse gas phase 3 stringency justification. We have a very challenging regulation ahead of us with greenhouse gas phase 3 in the US and globally, very challenging carbon reduction goals. And this technology fits that strategy very well. As I talk to end users, people that operate the equipment, the story is very common. They like the technology because it's the most diesel-like technology out there. It's the most diesel-like solution. It gets the job done. It provides the power, the torque. It can operate in the existing environments and existing equipment. It's very, very diesel-like. It's just zero carbon and very low NOx, which you heard earlier. And then finally, we do see this as complementary to fuel cells. It builds scale for the very expensive storage components. These tanks are expensive. It's carbon fiber, and they're very high-tech tanks. And so the more volume we can drive to these tanks, it brings down the cost overall. And so having both engines and fuel cells in the market can increase the demand for these fuel tanks. It also, having both technologies drives fueling infrastructure. The more technology you have that can leverage the exact same infrastructure as a benefit. And what we don't talk a lot about is service and support. Every new technology needs to be supported. And because both technologies, fuel cells and engines, are dealing with the same fuel, that's the big new thing for service infrastructure, being able to service these components, these products indoors. And then your investments need to be made, but those investments are very common. And so it helps, again, break down those barriers for adoption. Next slide. So as I wrap up my section, we're targeting a number of initial applications globally. So each of these represents either an OEM or an end user, which we have an agreement with in place, and you can see the diversity. You can see traditional on-highway, on-road applications on the top, and then off-highway, off-road applications on the bottom. Timelines vary per application globally, but in general, we're seeing things lining up for scale production in 2028, but it is infrastructure dependent. I can't stress how important that is. The combustion technology is rather conventional. Again, we know how to do it, but it takes fuel. And so That really is going to pace. We see the scale, the broad introduction of the technology is infrastructure, but the technology to consume the fuel can be ready in that time frame, and we're closely monitoring signposts on infrastructure. All right, thank you.
Thank you very much, Jim. Very nice. Next up is Ivan Tate, and Ivan is the head of product engineering and the technical center at FPT Industrial, and is coming to us, I believe, from Chicago. Ivan, good morning.
Hi, hello everybody. I'm actually in Pennsylvania this morning, but the experience for everybody will be pretty much the same. So normally I sit here and I explain who FPT is. You know, we're a so I say a fairly young brand in an old industry. But after a few years of doing this, and I think the caliber of our audience here and experience of our audience, I decided to go in a little deeper as to how FPT came into being, and really how our product has evolved and developed. So this is a timeline. It goes back a long time, you know, and it emphasizes we've had 100 years of development of engines. You know, we've been chasing efficiency, we've been chasing power. You can see the turbochargers coming into the trucks early on. And everything's been pretty linear up until we get into the 2000s. And much like everybody else, you know, we had a global footprint, mostly on highway, where driving legislation. And we see the first hybrid coming in there, and then we merge with CNH in the early 2010s. And you can see SCRs, expansion of our off-highway business, right through to late 2010s, where Stage 5, Euro 6, and other emissions, global emissions, China, India, really catching on. All big markets for FPT, really driving our technology and making us look for both standardization and solutions that are reliable across the world. In 2022, just to add another name here, we spun off from the CNH Industrial as Iveco Group. So buses, trucks, military vehicles, engines became separate from CNHI. You know, this led us to really reviewing our portfolio, reviewing our approach to the market, remaining more competitive. And that in part has driven us to develop our own corporate CO2 targets. So our goal here is really aiming for net zero by 2040. The next slide explains a little bit on how we plan to do this from our product strategy. On the left-hand side here, I guess chronologically in some way, we have to maintain diesel engine production. It's significant. There's a significant number of users, and also the technology needed to maintain that competitiveness of this technology that everyone accepts. In reality, everybody wants, or most people want, is going to keep increasing. You know, we're committed to doing that, both from a vertically integrated point of view and from a market point of view. We also keep a strong focus on alternative fuels. That started 35 years ago with natural gas. We sell a full range of natural gas engines on highway in Europe. This gives a second string to our engine development. It's also very, so I say, forward thinking from an off-highway point of view. We're looking at circular industries where farmers can produce their own fuel, burn their own fuel. Taking industrial waste or farm waste, and actually coming into a carbon negative situation for their fueling. And then finally, the subject of today, H2 internal combustion engines, a natural step forwards, as we'll see later, from the natural gas engine in particular, but certainly a very efficient way to have zero emissions at the tailpipe with any hydrogen and overall net zero depending on the source. As with any other manufacturer in our position, we've also had to diversify, increase investment in alternative parts of the vehicle that will support our expansion. So we're looking heavily into axles, control systems. We're making our own batteries and researching the benefits and capabilities of fuel cells for our market. If we, on the next slide, I thought I'd capture everyone's attention by putting some pictures of some whole machines. This kind of shows everyday applications. So again, we'll probably talk about the fact that our methane natural gas engines are a good gateway, and not only are they potential very low carbon energy today, they're a gateway through to hydrogen. So on the left, this is a tractor that you can buy on the market today, both in Europe and North America. You can buy it if you're a farmer with the right equipment on your own fuel. Well proven in terms of performance and a couple of years in some regions. And then we are also looking at the practical applications of H2 across a number of off-highway applications. We're running these engines. We want to get the feedback, like I said, servicing, life cycle, even operator experience. The only way we can do that is really starting very early and building that convenience into that product. Okay, thank you.
Great, thank you very much, Ivan. Appreciate that. Next up is Louise Arnold from Johnson Matthey. Louise has been with Johnson Matthey since 2000, with her current role being the Global Light Duty Product Line Director for the Clean Air business, a position she's held for the last 3 years. She started her career with Johnson Matthey as a process development chemist at the Tech Center in Royston, the UK, and has held various technology assignments throughout her career there. And she is the inventor on a number of patents in the field of emissions control catalysts. So Louise, thank you for being with us this morning.
Thank you for inviting me, Alan. So a little bit about Johnson Matthey. We are a global company, and our aim is to catalyze the zero transition for our customers and wider society. And we think it's very important that we, put our money where our mouth is. We say we're a sustainable company. So we have sustainable technologies, and we use our science knowledge to create solutions that really do make a difference to the environment and the people who use them. So a little bit of a change to our last two presenters. We are in fact a specialty chemicals company. And if you'd like to progress, Alan, we've been around for a couple of 100 years. Our background is the platinum group metals that catalyze many of the reactions that we're going to need for the low carbon future. We play in a number of markets. At the moment, emissions control catalysts for internal combustion engines is one of our leading markets. And we also are now growing in sustainable aviation fuels and the catalysts that are needed to be able to turn biomass into low carbon liquid fuels, and also in the fuel cells space, being able to enable manufacturers to make their fuel cells. And actually Johnson Matthey has a history in this area because we provided the fuel cell that allowed NASA to land on the moon. So a lot of history in this area. And I'm very pleased to say we have also been awarded various sustainability awards for how we run our business and the products that we generate. Alan? So what are we trying to do for our customers? Well, we're driving down transport emissions, be that from diesel engines, gas engines, natural gas engines, or hydrogen engines. And we're looking to make sure that the fuels behind them and the chemicals needed for all of these processes are driven towards sustainable feedstocks and low carbon wherever they can be. And in fact, transitioning and transforming our energy systems and trying to make that a truly circular economy. We are already the world's largest refiner of secondary platinum metals, and we have refineries around the world taking catalysts from the customers, from the industry, and re-releasing that metal back into the supply chain. So we work in a number of sectors, all of which are relevant, I think, for today. The emissions control systems that we've talked about being needed to make a hydrogen engine truly zero emissions at the tailpipe. The catalysts that are needed to maybe supply liquid fuels, and definitely the components going into hydrogen manufacture itself. So if you want to click through until all four back boxes show. So just this, I don't want to spend a lot of time here, but just to say we're working with a number of industrial leaders, looking at how we can generate sustainable fuels for the future, various products in biofuels and in hydrogen. So just to say we're playing across the board here, we're fairly agnostic, and we can talk about the benefits and opportunities of different routes to get to our low carbon future. So clean hydrogen, we see it playing a critical role in that low carbon future, particularly in those areas where it's going to be quite difficult to otherwise decarbonize. So we've talked about fuel cells in the future in the heavy duty arena, and also indirectly for sustainable fuels in, say, aviation, where putting a battery in an airplane, I don't think any of us ready for that quite yet. But the other great thing about hydrogen is, as we've said, it can almost be a drop-in for the current, I say almost, there's a lot involved in this, but it can be used in a very similar way that we currently do diesel. And therefore, this can be used as an enabler to get us to that even lower carbon future than the one we are anticipating at the moment. So hydrogen can be generated from a variety of routes, and it has pretty much a full rainbow of colors to describe the various routes. And I think that's available at some point during the discussion today. But depending on where that hydrogen comes from, it's going to have different levels of purity. But the great thing about a hydrogen combustion engine is it can use any of them. So as we progress to getting the maximum green hydrogen, so the one that's used from renewable electricity, we can enable the investment in the infrastructure and the market that's going to drive that demand much earlier than waiting for everything to be perfect at the end of the process.
Very good. Thank you, Louise. Forward to hearing more from you in a moment. Our last presenter this morning is Dimitri Konson. Dimitri is the Vice President of Engineering at Tenneco Clean Air. And good morning, Dimitri. Thank you for being with us.
Good morning, good afternoon, and good evening, everyone. Thanks, Ellen, for the introduction. Yes, I represent Tenneco. Tenneco, just like my colleague Louise, previous speaker, we represent suppliers, tier one suppliers and partners to the OEMs that are building engines and vehicles. Let's go to the next slide. So Tenneco is viewing themselves as a partner. We provide solutions to our customers, and this partnership idea can be seen in our vision. We want to be the most trusted partner and the world's best manufacturer and distributor in the transportation industry. We're a big company. We're almost $20 billion in revenue. We got tens of thousands of employees, dozens of engineering centers, lots of manufacturing sites. I'm not going to go through all the numbers. You can see them on the right of this slide. Let's go to the next page. So first and foremost, Tenneco is a powertrain technology company. We believe in the future of internal combustion engine and its place in providing cleaner transportation options to the society. And our offerings to the industry include components, engine components, anything that moves almost in the engine and provide the spark ignition, or routes the exhaust gas and treats the exhaust gas to the tailpipe. Virtually everything in between the combustion cylinder to the tailpipe, we provide those solutions to the customers. We partnering with a lot of organizations, from the customers to the research institutions to academia. We invest significantly, including in this case in the hydrogen internal combustion engine, in terms of labs, the new research in materials, system integration, and simulation capabilities for it. So all of these components that are listed here and the elements of the after treatment has some relationship to the development that we're doing on the H2-ICE, and that represents our investments and commitment to the industry to deliver. Let's move to the next page. Yeah, so why do we see hydrogen engine as part of the future mobility? We see it as the most pragmatic near future step towards decarbonization of commercial fleets and off-road machinery. That's already been said, but I just want to emphasize that for a relatively modest incremental investment in technology, H2-ICE can deliver a substantial step function reduction in CO2 and other criteria pollutant emissions. It's really a practical way forward for the industry, for the society to really get the benefits of it. Because of course the emissions are much lower, and CO2 tailpipe emissions are near zero, but really we're talking about trace amount of CO2 that is for all intents and purposes negligible in the big scheme of things. It's affordable solution, it's scalable solution, it's the reliability, durability is proven, and it's demonstrated compared to other decarbonization options. And the industry is ready. We certainly feel that Tenneco is ready to step up and support our customers and the industry with the systems and components. We see many proven solutions that are transferable or easily adaptable to H2-ICE. And I talked about the partnerships that we built. We're making a lot of investments, and we're ready to collaborate with any credible partner who is looking to make progress in this direction. I think that's my last page. Turning it back to you, Alan.
Great. Thank you very much, Dimitri, and to all of our presenters. Just a reminder for our attendees, you can please use the Q&A box to submit questions. And I see a few of those coming in, and we will get to some of those topics here as we go ahead. Okay, so let's dive into some of the details a little bit. I'll just say a few words about hydrogen, the fuel. I think that we all understand that there's considerable development needed to expand the availability of hydrogen as a fuel. It's certainly available, has been available for a long time. And of course, it is the fuel that's powered the NASA rockets and shuttles to space for many years. So it's not a new thing. Will be a new thing for some of the transportation sector we're talking about here today. The Inflation Reduction Act provided about $8 billion in funding assistance to drive development of hydrogen hubs throughout the U.S. I think that'll play a key role in making the availability of this fuel something that the internal combustion engine users can take advantage of. One of the reasons hydrogen is so attractive is part because of its energy density. It has ability to deliver, as has been said, great performance, much like that of existing technologies. We do know that all hydrogen is not created equal, and you've heard reference to green hydrogen here today, and of course that's at the top of the list in terms of preference and impact on climate and other emissions. And there are a whole range of other forms here, and these are labeled by color, and it's I'm gonna say quasi-technical, but you get the idea that there's great diversity and different kinds of sourcing of hydrogen and what happens to byproducts in the sourcing process, etc. So with that, let's jump into a little bit bigger discussion about the fuel. And we've got a couple of questions here we'd like to get some conversation going on. And I think we've touched on a little bit of these, but let's focus in on the fuel now. And we have some questions here about the major issues surrounding hydrogen as a fuel, why it is a good fuel, which applications might make the most sense, and what are the barriers really for getting, from a fuel perspective, getting this in the sector here. So let's begin our discussion with that. And I think, Dimitri, you have a slide next that we'd like to maybe talk about a little bit, start that conversation.
Yeah, for sure. This is a map, if you will, that looks at different transportation options in terms of range and power, right? So you see, high power and, medium and high range, and at the corner of the chart, you can see battery electric. Battery electric is certainly a great option for anything that has low to medium power requirements and doesn't have the range that exceeds or pushes the boundaries of the battery technology, right? Plus, you need some ability to pause whatever you're doing to recharge the battery, and if that could be done during some kind of a nighttime, that's perfect. Now, fuel cells are now allowing the same function as battery electrics to be extended to a longer range, right? You certainly can be refueling in a lot more practical way for it. You could certainly produce have the power source as you are pushing that range. At the high power and especially high range, you need something that is has good energy density as a fuel. It has practical refueling capability, right? It has robustness and durability. And in some cases, when we talk about construction, agricultural applications, some insensitivity or robustness to impurities in the fuel as well. So that makes H2-ICE as a really a perfect solution for this high power and either stationary or high range applications. It's as Jim mentioned at the beginning, it's not a competing technology. It's not necessarily a transition technology. It's a complementary technology to other decarbonization options. That's how we see it.
Others want to comment on the fuel questions here. I did want to ask one about fuel quality. I think, and Louise, you pointed this out as others have, about the variations in fuel quality for hydrogen now, and the fact that internal combustion engines are maybe more capable of handling different qualities of fuel. And Dimitri, as you just mentioned, levels of impurity. I'm just curious about that, and sort of how does the engine have a sensor in there for the quality of hydrogen, or do we assume that it's a certain level of purity? How does that work?
Well, I can talk to it not from the engine side of things, but certainly how we would deal with the emissions from that. Now, my understanding is whenever we're talking about any of these different varieties of hydrogen, the actual impurities are quite low. And for all of these systems, we will be putting an emissions control system on the end of it. And that will make sure that tailpipe will be as close to zero as you could possibly, and we're talking the fourth decimal place here, possibly measure. We're talking ppm amounts, if that. And that will be using, depending on say the oil combustion predicted in an engine, we'll have a small oxidation catalyst, possibly a filter, and also some SCR catalyst that will reduce any of the NOx generated during that combustion process. So we will have an after treatment system that will be similar to many of the systems that perhaps are on the road today, but will be tailored to the temperature ranges, the duty cycles, the flow rates that we will see from these new engines. So as we are today, if you take your modern, fully equipped vehicle through a polluted area, because it intakes that air from its surroundings, what's coming out of the tailpipe can actually be cleaner than what's going in. So we would anticipate with the modern technologies for those emissions control that what's going to be coming out of the end of that tailpipe is as near to zero emissions as you can measure.
And Louise, that's going to be more simple than the equivalent diesel engine. So
Yes.
can meet similar emissions targets. From a packaging point of view, we may be trading space, exhaust space for tank space, fuel space, but certainly keeping probably a similar level of complexity to the vehicles today rather than increasing it.
Yeah.
And I can add a comment on the fuel quality. And so we an engine is more tolerant of contaminated hydrogen, and it's only because a fuel cell is very intolerant. It's an electromechanical device. Any contaminants in the fuel can actually contaminate the catalytic plates, reduces efficiency. That's why we talk about fuel purity so much with hydrogen, because of the fuel cell. The engine, because it's combustion, it is just inherently more tolerant. I did see a question in the chat around NOx emissions, and so kind of tying it back to some of that previous conversation. H2-ICE inherently has a lower engine out NOx signature. Just the way that the process works, it is inherently a lower NOx out of the engine. Therefore, the after treatment technology required to further reduce NOx it requires less work to knock down the final NOx. In the question, it does relate it to state of the art diesel, natural gas. In general, natural gas engines are stoichiometric, and they're using a three-way catalyst for NOx reduction. Cummins, and I think in general the industry, seems to be using SCR and lean combustion, lean burn technology for the H2-ICE engines. Therefore, SCR is the after treatment technology. And we see H2-ICE being able to meet all future regulations out there. And again, it's an easier step to reduce it. So very, very low NOx. And at steady state, I mean, it's at the ppm. So think about power generation and steady state applications are just near zero inherently, even engine out.
Sticking with the fuel just for a moment, we have an image here of a fuel pump for hydrogen. Can we, and Jim, I know you showed a number of different applications that Cummins is working on today. Can we expect, what are you telling your customers about the hydrogen fueling experience? Is there anything special about that folks are going to have to worry about?
Standardized interfaces, we would expect that. And it's really only pressures is what comes to mind. There's two different pressure nodes that are in the industry, 350 bar and 700 bar. 350 bar pressure is more available today, but we do expect 700 bar in the future to become prevalent because of that increased density on the vehicle. But from a filling perspective, filling the vehicle will be the same process between a fuel cell or an engine. You wouldn't know the difference. The operator wouldn't even, the only difference you could tell is that you might hear an engine run and you might not hear a fuel cell, but otherwise the experience is the same. So yeah, very, very common. And there will be a fuel grade. That's maybe one more thing I should say. There is a fuel cell grade and an engine grade, ISO specs being worked on. I think we would recommend most stations and plan for a fuel cell grade just because it helps, and the engine can run on either. It doesn't matter. It's just hydrogen.
Okay. Maybe a last question relating to fueling is because of those extreme pressures, I know that folks are thinking about what kind of vessel needs to be on board a vehicle or machine to accommodate the fuel in a reasonable quantity for that machine or vehicle to do its job. What are we talking about in terms of size of fuel tanks and storage to get, sort of equivalent kind of performance? Is it much larger, much less? How does the weight maybe compare at this point?
I can make a couple comments. For a traditional kind of heavy duty line haul truck, we're targeting about 80 kilograms of hydrogen on board. And that is an equivalent to about a 500-mile range in most applications. Obviously, that varies dramatically based on what you're doing. But that 80 kilograms, we feel like we can package in typical back of cab style It would look like very similar to a natural gas truck. You know, you wouldn't even be able to tell the difference from looking at the tanks, though they are thicker walls because of higher pressure, and they will weigh more. So there's more carbon fiber, there's more weight because for the hydrogen tanks versus natural gas. Off the top of my head, I feel it's been a while since I've looked at the weight numbers. It's in that 2,500 pounds, I believe, extra kind of at a vehicle level. That's just a rough estimate. And we would expect that, like, there's a weight allowance today for alternate technologies, like natural gas truck has a 2,000 pound weight allowance. If it's a natural gas, therefore you can haul the same amount of cargo because it's compensating for the weight of the tanks. So we would hope that similar Department of Transportation regulations would apply, and you could have that weight allowance to enable this technology to not reduce cargo capacity.
From a real estate point of view, we're probably looking at something like 5 times the area of a diesel tank in terms of volume, rather than the mass of the fuel or the mass of the tanks.
Yeah.
So certainly, maybe in the on-road truck, maybe buses, there's plenty of real estate. If we look at our big off-road consumers, so something that would that will drink 1,000 liters of fuel in one go, one operation, one day. You know, we still have packaging concerns that, and certainly the cylindrical vessels are more difficult to package as well. You know, fuel tanks have become very efficient. They mold around things, they mold around steps. But we, you know, looking across other applications, we've got to really work at the packaging and maybe use some technology to kind of hide the tanks, or put them in sight lines and use cameras and screens instead, those kinds of things. So we could be seeing some architecture changes from a superficial point of view on the machines.
Okay. Anyone else want to weigh in on any of the fueling issues? Okay, well, it seems like the biggest challenge really is to make that fuel available and getting that to places where customers can access it. And it sounds like that is also a process underway. Let's turn now to the engine, if we might. There we go. And this is where we've had already a little bit of discussion, but we've also had a number of questions coming into the Q&A section there. And many of you have touched on some of these aspects already, but I wanted to just, you know, kind of tee this up here. So we've heard a lot about how H2 engines compare to gas, diesel, and sort of what that looks like. And you know, I think now really what are the main challenges we have as an industry to produce those engines and get those into the marketplace. And how do they compare to the competitive technologies? We've heard a little bit of that, but hopefully this part of the discussion will get into that a little bit more. I think we have one slide, or a couple slides, and with you, Ivan, maybe going to take the lead to start our conversation on this.
Okay. Yeah. So this I started off earlier, you know, kind of highlighting the experience from natural gas. Kind of was a gateway to hydrogen, basically because the cylinder head, the spark plugs, the valve layout, it lends itself, although, you know, there's some design changes needed, certainly lends itself better than the diesel straight compression ignition, where you may need to pilot with a different fuel. So, you know, really looking at using hydrogen as the solution rather than a mixture, which again may be another step towards getting to the end goal of net zero. You know, we take our standard engine, certainly structurally, the engine block, the basics on the head design, and the fact that it's a number of pistons going up and down and a crankshaft rotating coming out the back. That's all pretty much straight carryover. Where we do see a lot of development work going on is both in the combustion realm. So, you know, you can see new piston design here, and the head, certainly not to be underestimated. Like we said, depending on what you're trying to achieve, you know, there's a few different methods to inject the fuel. And certainly there's many different ways to make sure that the burn happens as you want, at the speed you want. And then there's also not only the tanks that you have to consider, the fuel distribution, but it's putting the fuel into the cylinder, and that's really where a lot of the work is happening as well, to create long-lived, reliable fuel injection systems. You know, the development of the Common Rail fuel system happened over many years. Pressures increased gradually. Much like everything else, we're trying to start running here from the very beginning. So a lot of work's going in on fuel systems. Then touched on it earlier, simplified ATS, and then very similar control systems, same ECUs. Some of the engines we're running today are running the same basic electrical architecture that our diesel engines have, with modifications, so we can get these demonstrators up and running and learn from them. So I think that emphasizes the simplicity of this. It bolts into existing platforms using majority of existing engine components.
You have one more slide there.
Okay, so this is really taking a look. It covers a bit of what we've looked at before. You know, obviously the fuel cell is seen as, I'll say, the competitor here in terms of the trade-offs, but we know that they're good solutions for different applications. But certainly, as we use existing existing gas distribution methodologies, we may see hydrogen purity being affected, and certainly that wouldn't make any impact on the ICE engine, maybe slightly slower response or power outputs, but certainly wouldn't cause permanent damage. We can control the CO2 based on the fuel in the same way, and then pollutants, although not zero, we can get near zero. So the actual benefit, particularly from a carbon emissions point of view, is equivalent. What we all like, I think, is the fact that the payload and the vehicle architecture remains very similar for the ICE engine. And that includes also drivelines. So we're not looking at you know, a partial hybrid system, or we don't need a partial hybrid system or a battery storage, energy storage that can try and keep your fuel cell operating in the right conditions. And then environmental usage, you know, we see a lot of this won't tow a trailer over over I-70 pass at 60 miles an hour or whatever else, because it's minus 20 degrees C, or you can't cold start, or it's too hot. A lot of those are very manageable with the standard combustion engine setup, along with taking it straight to your existing dealership or network. You don't need high voltage training. There's no special tools, and if they're natural gas certified, then it's just going to be an extension of that.
Very good. I think, Louise, I think you had some additional insights on this question about the emissions control as well.
If I can find the unmute button. So yes, so just a little bit thinking about the after treatment system. So as we've just said, operates very similarly. So if you look, the schematic we have on the right is almost a simplified sort of European type system that we could see. You've got the oxidation catalyst that will deal with any hydrogen slip. I think somebody on the Q&A asked that one. Then that cleans up the exhaust to go into the reduction step using urea. There could be an ASC there as well, which would deal with any overinjection of the urea potentially. And then if needed, a final small particulate filter just to clear up any particulates that may have been either generated by the engine or generated by the after treatment system itself. So the system at the moment, and I also have a slide that shows we're working with a number of customers with various variations on these sort of iterations around current design technologies. So as we can see, we've got a few sort of potential offering dates there. I think those 2025 numbers are a little ambitious, but you can see there's a range of architectures, more around the sort of traditional architectures. The one at the bottom there, we're working with one of the customers, is an SCRF. That's commonly seen in light-duty diesel applications in Europe at the moment, with then that ASC catalyst at the end that would deal both with any ammonia over injection or small amounts of carbonaceous materials. So there are a number of ranges here. It will depend on your packaging constraints. It will depend on your individual architecture of your engine, the emissions pertaining to that individual engine, how you design, how it goes bang influences what comes out of it. So at the simplest levels, we help to then tailor the emissions control system to deal with those emissions. So I think, you know, that hopefully also answers a number of sort of the general questions that I've been seeing in the chat around emissions control after treatment. I did see one about ammonia. Now, my understanding at the moment is ammonia is more being thought of as sort of a marine solution at the moment, rather than an on-highway sort of solution. But who knows what will happen in the future? But that's my understanding.
Okay, let's go back. Go ahead.
I can maybe add a couple of items here that you know, I think Louise gave a pretty thorough explanation of the options and the after treatment and the catalysis required for it. Maybe just to kind of put things in perspective, right? The hydrogen itself does not have any nitrogen to produce NOx, right? The only nitrogen that really appears in the exhaust is the nitrogen from the air that is part of the combustion process that is coming into the engine. So the amount of nitrogen is small. The other nuance of hydrogen combustion is that it produces water naturally, right? That's the natural product of combustion of hydrogen. So that water creates some challenges for DNOx after treatment, but again, with the right thermal management coming from the engine and the right selection of the catalyst chemistry, this could be overcome. So overall, I think there was a question about the complexity and cost of after treatment for hydrogen ICE. The cost is going to be trending down, I guess, from the baseline of a diesel after treatment, just because of the complexity reduction, and as the kind of consensus in the engine world reaches, you know, what kind of combustion, what kind of fuel injection is going to be used, you know, the variants and the flavors of after treatment are also going to converge to maybe a smaller number of options with lower complexity. That's how I see this going.
Thank you. Others want to weigh in on this question? We're seeing a few questions here in terms of this area, so I'll just pick out one of these at the moment. So one of them gets to be a question about durability and life cycle, H2-ICE versus a fuel cell that's using hydrogen, of course. Does anyone have any perspective on that, whether or not there might be a difference? I know, Jim, you guys are looking at both those solutions, as you are as well, Ivan. Any thoughts on that, Jim, to start maybe?
Yeah, sure. We're targeting, I'll start from an engine, you know, our durability expectations are the same for, you know, lifetime of a combustion engine on either fuel. And fuel cells have different degradation modes than an engine. And, you know, designs are being worked to increase the durability. You know, the target is to have systems that are durable to the full life of the, you know, the vehicle expectation. But they're, you know, fuel cells are still in their evolution. Fuel contamination is a challenge. as we know, and air contamination. They just both can reduce the efficiency of the fuel cell stack. And so today's systems that you might be able to purchase on the market today may have a replacement life to meet that full, but the target is that future versions of fuel cells would meet the same expectation as an engine today.
Yeah,
Okay.
I think it's safe. I'll try and speak a bit closer here, but it's safe to say that the idea is that from a dollar to dollar or pound to pound or euro to euro cost per hour on that capital investment should be realised across the products. It should be equivalent. Certainly, the fuel cell, if it requires slightly more investment, it needs to be in the right application, and you may be able to realise that and see an equivalent cost of ownership as well. So then, if we're talking about time, materials, embrittlement, or permeability of materials as well, there may be a certain amount of servicing needed, or refreshing of the product, much in the same way as today, whether transmissions, engines, after-treatments, filters need changing or refreshing. You may see a similar kind of recommendation from a service point of view as well to keep things running.
Okay. Very good. Thank you. Anyone else want to weigh in on that? If not, we're going to go right into our Q&A. Whoop, I'm sorry, I'm a little too fast here. So we've got a range of questions here. We have about 15 minutes left to try and get through these. Let's see. We'll start out with maybe just a simple one. I think, and maybe this has been touched on a little bit, but what about the level of training necessary for mechanics to work on a hydrogen internal combustion engine? And I think someone might have covered a little bit of that already. Anything different? How does it compare to what we have today?
To me, the biggest thing it'll be the fuel delivery system. I mean, it's an engine still. It has injectors. It does have a spark plug, which is new for maybe the market, but otherwise it still does have shares common architecture elements to a combustion engine. So there would be unique training for each engine, but in general, it's similar fuel delivery system. The maintenance, ongoing certification, and high pressure lines would be the new area. But again, a lot of similarity with the fuel cell fuel delivery system, which would, it's very, very common.
Okay. There was a question about the thoughts about creating hydrogen on board the vehicle from hydrolysis and retrofitting existing diesel engines. Anyone want to take on that question? Do we see retrofit of hydrogen into existing diesel engines happening anytime soon?
From a Cummins perspective, it's a great question. We would love for the answer to be yes. In general, a retrofit is a big deal. From the engine itself, you are changing compression ratios. You need a spark plug. There's a lot of physical, software. So from an engine, it's a big change. Second, the vehicles typically are not set up to support the fuel delivery system. The frame's not long enough, and so when you get into it, the costs of doing the retrofit are significantly more than just a brand new vehicle. There could be exceptions to that in certain applications where you could swing a system in, but a lot of times it does just become cost prohibitive.
Yeah. Another question coming in here. This is gets into a little bit of an area that is somewhat related to what we have today with diesel engines, for example, and their ability to use varying blends of renewable biofuels.
Mm-hmm.
But the question is, what sort of fuel agnostic engine solutions will be available in the future to tolerate varying ratios of hydrogen and methane fuel blends? Any thoughts on that one?
So if my microphone's working, certainly hydrogen, and mixed fuels are interesting, because we're talking about using the transition, using distribution networks. So you've got a choice of mixing at source or mixing on the vehicle, for that matter. That may, in answer to the previous question, may be a retrofittable activity to a certain degree. From a certification, from a incentives point of view, or even from an emissions classification point of view, obviously retrofitting becomes far more difficult.
Okay.
I can get unmuted. From a catalyst after treatment position, that also gets very interesting, quite complicated, because I think, Jim, you might have explained, for a CNG, a natural gas engine, we use a three-way catalyst that does, it operates around lambda-1, it operates at very high temperatures, it does both oxidation and reduction at the same time. They are much more expensive for the level of PGM that you've got on there, the precious metals, and converting methane is a bugger. Sorry to use that language, but it's an incredibly stable molecule. You've got no way of getting into it. So converting it is just a pain. I've been working on this for 20 odd years. Somebody can write me a simple answer. I'd be very, very happy to hear it. And then if you look at the hydrogen side of things, we're going to be using a more sort of oxygen-rich environment, that lean environment that we've been talking about, and that has a totally different system. It has a smaller oxidation catalyst, which does, just oxidation, and then you inject the urea to do that secondary reduction chemistry. So blending those two things together, I mean, it's a great challenge. And I think I can see a path to do it, but it's going to make that after treatment system much more complex.
Okay, thank you. Here's another one. There are diesel internal combustion engines delivering a few megawatts. Do you expect hydrogen ICE or fuel cells to reach these power levels in the near future?
To me, it's just a market-based need. There's no technical reason why they can't at all. And I think, for data centers and other very large applications, I think we'll see both technologies in those applications.
Okay.
I think one of the other questions we've had is about the cost of the various routes to hydrogen. And a lot of them could come down to, what is the cost of electricity in your area? And in the US, we've got obviously a mixed grid. Some have got more renewables, some are still coal-based. So again, how green is your electricity? How green would your hydrogen be? As you're looking around the world, there are different solutions. If you've got a lot of geothermal energy to get very green electricity, maybe you'd go a different route, and maybe the price of that electricity or those comparative fuels are going to be different. So economies of scale will also start impacting this. So it's going to be a moving target as we go forward, as we decarbonize the grid and we decarbonize various other areas. Some arguments say, oh, well, carbonaceous fuels are going to get cheaper because we're going to have an abundance and an oversupply. Well, I should imagine that we'll see decommissioning of refineries and a reduction in that supply chain commensurate with the usage, as we see further investment in greener electricity generation. So it's going to be a moving target. It's going to shift. It's going to depend on the market you're operating in. So again, that points to a pragmatic solution. I know one of my panelists use that word a lot, and I think it's very important to look at a pragmatic solution. And I think I see hydrogen combustion engines as an enabler of the infrastructure to create a pull. They are relatively agnostic to the color of the hydrogen that you're generating, and also therefore the price that you're using. So if you were moving across a country, you could potentially use different grades of hydrogen if there was a particularly different price point potentially.
Okay. All right. I'd like to move into our final thought section here. We have about 5 minutes remaining, and just offer each of our panelists the opportunity to make a few closing remarks about this topic. And we'll start with you, Jim.
Yeah, sure. So thanks again for hosting. It's been a great discussion, and I'm just really excited to see this group together, to having this discussion, and the support we see around the world for the technology. We're seeing multiple governments around the world supporting it from a carbon reduction potential. The industry, just the number of manufacturers in the industry that are supporting the technology just shows the interest and the viability, and then the customer feedback has been phenomenal. And so we're really, the fueling infrastructure is going to be the next key. But I'd like to just encourage the broader community to continue to support this. It's a critical technology. We need all options, and we shouldn't be deselecting anything at this point. We really need viable options to decarbonize. Thanks.
Thank you. Ivan, you're up. You're on mute. There you
Yep. So to follow that up, we hear a lot about there's many solutions, no one size fits all. But what we're dealing with here is a very practical solution. It's not in production yet, and I think reading through a lot of the other questions that are coming in, everybody's picking up on some of the challenges, some of the work that we're going to be doing over the next few years to make sure that this can work. But it is a very realistic step forwards for many parts of the industry, be it on highway, off highway, power generation, or marine. And certainly we need to chase these carbon reduction technologies and dedicate a lot of energy to this, highlighting vertically or horizontally the problems to the relevant industries and trying to close those questions out to allow this to hit the market.
Very good. Thank you. Louise.
So I think, we've talked about the solutions that we're bringing as suppliers or industry, engine and vehicle manufacturers. Ultimately, infrastructure is such a big thing, it can only be funded or driven by government choices and decisions, wherever you are in the world. So that's where we as a community, as taxpayers, as people who breathe the air around us, and people who operate vehicles, we've got to talk to our leadership and actually, have that conversation. There are going to be, as we said, a need for a portfolio of solutions, and we will continue to provide that portfolio of solutions from the companies and others like them that you see in front of you.
Thank you, Louise. And Dimitri.
Yes, I just saw a question out there that is kind of wondering about how do we respond to those who dismiss the hydrogen ICE just because there's a tailpipe. My answer to this is that really combustion is not the enemy. It's the CO2 and the emissions that's the enemy. And the solutions that the industry is developing are well suited to really deal with those emissions and providing a carbon free option really in very short term. And the answer is not just for maybe the idealists who think that way, but just from the policy standpoint, there needs to be alignment, and policies really connect things that otherwise would take a long time to develop and synergize together. That applies to the production and distribution of clean hydrogen, but also building the demand for technologies like hydrogen ICE as acceptable and desirable for the decarbonization in the future. If you look around the world, in Europe and China and Japan, Korea, hydrogen ICE is being recognized as a zero emission vehicle technology, and refueling infrastructure is growing rapidly. Certainly, I think it would be a missed opportunity if this technology, which has the potential to drastically reduce CO2, is not going to be recognized as an acceptable zero emission solution. So again, we need to kind of focus on what the real issue is, and I think the industry has all the tools to address it, and it's a great path to move forward.
Thank you all for those final thoughts. That was excellent. Everyone, I think, hit on the very key points about the future for hydrogen in internal combustion engines. And thank you all for joining us. All the attendees are going to get an email with a link to get the recording of today's event. We welcome your feedback. Any form you'd like to share with us about today's session, you can send us an email at that address there. We do have other virtual events that we've done this year, and those are available online. You can view that on our YouTube channel, which is accessible through our website. Next week, we'll be speaking down in Washington, D.C. on Capitol Hill as part of a policy forum at the EESI Energy Expo and Renewable Energy and Policy Forum. So if you have a moment, you can tune into our live stream there. But I want to thank all of our panelists today, Jim from Cummins, Louise from Johnson Matthey, Ivan from FPT, and Dimitri from Tenneco. Excellent discussion. These are the real leaders in the field of hydrogen internal combustion engines. So really appreciate all you're doing and for sharing that with us this morning. So with that, I think we are done and right about on time. So thank you all, and we'll look forward to next time we're together. But please have a good day. Thank you.